A 14 billion parameter open-source model trained for under 12 hours on a single GPU just edged past GPT-4.1 on a Biomedical coding benchmark. This wasn't a multiple-choice exam. To win, the model had to write code, query electronic health records, and debug its own runtime errors to prove the program actually worked. The human architect, who has been tracking the MedAgentGym research, argues that this result represents a shift in how we approach medical AI. It suggests we should stop treating model improvement as a knowledge retrieval problem. The strategy involves training an AI agent much like a robotic system. You place it in a domain-specific environment where it can act, fail, and improve through verifiable feedback. This 14B model reached parity with a frontier giant using a fraction of the typical compute. It points toward the training environment rather than raw scale as the primary lever for specialized performance. The MedAgentGym functions as a specialized Docker sandbox. It comes preloaded with biomedical packages and operates under strict partially observable conditions. The agent navigates using 4 core actions. Request info pulls critical data like EHR schemas, while terminal handles dependencies. Code execution runs generated scripts through a live interpreter. Finally, debugging translates raw runtime errors into natural language explanations, giving the model context to fix its mistakes. The environment is physically constrained. Sessions are capped at 15 turns, and a strict 120-second runtime, forcing the agent to find efficient solutions. These mechanics transform the benchmark into a computational teaching hospital, where the model must troubleshoot clinical data in real time. Think of a developer who keeps trying the same broken solution because they cannot recognize they are repeating themselves. This breakdown of GPT-4.1's performance reveals a massive bottleneck. Over half of the errors are caused by getting stuck in loops. Runtime errors make up the next 30%, representing failures during execution. The remaining mistakes are split between compile, input-output, and miscellaneous glitches. These loop failures suggest that even frontier models struggle to maintain adaptive control over a multi-turn coding process. The data suggests that the primary barrier for these models in specialized domains is process management, as the models clearly have the underlying medical knowledge to succeed. There are 4 primary ways to train these capabilities: imitation of correct examples, choosing between preferred options, trial and reward, and rewarding the best group variations. The unoptimized Quen 14B base model begins with a low zero-shot score of 20.12. Supervised fine-tuning provides the first significant jump. By imitating 1,000 correct examples, the model reaches 63.92. Adding direct preference optimization, where the model learns to choose a better answer, only provides a minor gain, stalling out at 66.37. The trajectory changes when we introduce online policy gradients like PPO, climbing to 69.56. The final step, group relative policy optimization, reaches 71.42. This narrow win proves that a 14B model can outpace GPT-4.1 when trained on these specific domain tasks. Passive imitation reaches a plateau quickly. Active online reinforcement learning is required to clear the threshold of frontier performance. This specialization comes with a penalty. It is the AI equivalent of a chef who is elite in their own kitchen, but becomes average the moment they use different equipment. On the left, we see the model winning in distribution, but on the external out-of-distribution benchmark, that 71.42 score drops to 47.02. Models trained purely on imitation and offline optimization showed almost no improvement on these external tasks. The knowledge they gained was brittle and confined to the gym. On these adjacent tasks, the generalist models regained the lead. Both GPT-4.1 and GPT-04 Mini outperformed the specialized 14B model once the environment changed. The victory inside a curated gym is currently bought at the price of broader generalization. Real transfer remains the primary hurdle for specialized agents. This creates a tension between 2 philosophies: the pursuit of broad generalist models versus the development of narrow, domain-tuned specialists. Generalist proponents argue that medical tasks are interconnected and multimodal, meaning a single large model can generalize to new problems without specific fine-tuning. However, the MedAgentGym paper found that highly specialized medical reasoning models actually performed worse than their own base models in an active environment. Standard fine-tuning on static medical QA datasets appears to degrade a model's ability to follow dynamic instructions. specialization must be environment-based to be effective. Static datasets often damage the very utility they are meant to improve. The 14B model succeeded because the MedAgentGym provided dense, executable feedback at every turn. While static training offers sparse signals, an executable environment creates rapid, verifiable loops. The model learns from code that either runs or fails. You cannot compensate for a lack of feedback by simply increasing the parameter count. For specialized domain work, feedback density is a higher leverage variable than the size of the model. If you want more analytical breakdowns of the research moving the needle in AI, subscribe to the channel. Comment below with the next domain where you want to see a specialized gym applied, whether it's legal, in global finance, or complex engineering. Keep that 50.39% in mind. Half of the errors from a frontier model were just infinite loops. The future of specialized AI depends